All right, welcome back for part two of the product rule lesson. Um, this one, use the product rule to differentiate this thing. So how are we going to write this? This is g at x to the exponent 2. Well, why don't we do what we just did there? So if I write p at x as g at x times g at x, then it's familiar because how do I take the derivative of that? Take the derivative of the first thing, write down the second thing. Plus write down the first thing, derivative of the second thing. Well, these are the same expression. So I got two of those same expressions. I have 2 g at x, g prime at x. And so notice that it doesn't matter what g at x is, I have this expression. So if g at x happens to be whatever this thing is, x squared minus 3, then p prime at x is equal to 2 of those black squares, times the derivative. Well, the derivative of that is just 2x, and so I write down the 2x. And I'm not going to simplify it. I could, I suppose, expand this all out, but I'm going to leave it like that because we're pattern hunting here. For the second one, well, we got 3 of them, right? This seems a little bit silly writing all this out because we just did it with the extended product rule, but let's see if we can find a pattern. The derivative, write down the first one, or sorry, derivative of the first one, write down the other two. Plus, write down the first one, derivative of the second one, write down the third one. Plus, write down the first two, derivative of the last one. So that means the derivative, I got 3 of the same expressions. I have 3 of g at x times g at x is g at x squared times the derivative. Huh. Exponent, exponent. Okay, something's going on there, and we're going to see if we can figure out this pattern in a second. But let's see. Trying to squish. I'll squish this one in on the side here. Here, this time, my black square, my g at x is this long expression, and so my derivative is 2x minus 4, and so p prime at x is 3 of those big black squares, and the big black square is x squared minus 4x plus 5, and then that squared times the derivative of the inside. There. Dandy. You seeing a pattern here? This is very similar to what we saw, and you don't have to write this part down, but we saw at the beginning of all this sort of thing, if I had an algebra term like this, the derivative was just the exponent came down, and then I subtracted a number off the exponent. That was the power rule for polynomial expressions. And it seems like it's very similar, except for if this is a black square in here, it stays the black square, but then I have to do the derivative of the black square at the end. So this one, p prime at x, the 4 comes down, the inside stays the same, that's the black square, the exponent goes down, and then I got to write down the derivative of the inside thing. And that is this whole long thing, except for if it's the same function. This is the extended product rule. And so if I had this in general, this is kind of hard to read here, if p at x is a power of another function, then to take the derivative, the exponent comes down, I write down the inside thing, subtract 1 off the exponent, then I got to take the derivative of the inside thing. Okay, and that's the power of a function rule. And now here comes some examples, a little more difficult. Do I have it? No, it's attached. I'm going to think of this then, because this is a hard one. I'm going to think of this as v squared, u squared. Let's say u squared. No, not U, and because they're hard to tell. When my U's and my V's look the same, I'm going to use M's. This is M squared, and this is N to the fourth. And so how do I take the derivative of this? Well, and this is just the way I'm thinking of it, by the way. This isn't actually N. If I want to take the derivative, right? The derivative of the first thing, which would be 2, basically 2m, and then m prime. Well, the m happens to be a bracket, right? Now, what's the derivative of the inside thing? The derivative of the inside thing is minus 4. But this is the first function. So the first function I just took the derivative of. That's the first function. And then I got to write down the second function, right? Write down the second function. I got to write down the n to the exponent 4. Plus, and I go back to the first function and I write it down. I write down 1 minus 4x all squared. That's like the m squared. And now I got to take the derivative of the second part. The second part, well, here the derivative of the 4n cubed, but then the n prime, right? Well, and this is just in my head. I'm not actually going to write this down. It's poor style, but this is what I think. I think of it as another function. So 4 comes down, write down the inside thing, and then n prime, the derivative of the inside thing, well, the 1 disappears, the 2 comes down to multiply by 5, that's times 10x. Squared becomes 1, and then dandy. And it says do not simplify, and I'm pretty happy that I don't have to simplify that, because that would be nasty. All right, onwards and upwards. So this looks actually easier. If I think of this as the first function and this is the second function, to take the derivative, well, I guess the square root's a bit of a pain, isn't it? If I think of this as the first function, I often like to think of this as an exponent, a half instead of a root. So the derivative of that would be the half comes down and then subtract the half. Okay, derivative of the first thing is this, and then write down the second thing. Times, not times, plus, write down the first thing, derivative of the second thing. This is in the way. Get out of there. Derivative of the second thing. Well, g prime, well, that's just a polynomial function. This is starting to get old hat. And then if I wanted to, I could multiply this all out and collect like terms, dot, 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 but luckily I don't have to simplify. I want to mention this. We could have taken the derivative of this after our first day with derivative shortcuts. Because if this is just x to the exponent of half, it's pretty easy just to write this as x to the exponent of half, multiply it through, and then take the derivative of that, right? The exponent comes down, subtract 1 off the exponent, and are these two expressions the same? If I were to expand and collect like terms, and indeed, indeed they are. They're actually exactly the same thing. And what's the moral? The moral is, if it's easier, do it that way. If this is easier for you, do it that way. The product rule, you know what? Product rule is pretty complicated. I couldn't see how we wouldn't want to expand that and write that in a different form. We'd have to use the product rule. But that's pretty nasty compared to this is pretty nice. So, think about rewriting the function first. How are we doing? Example 5. Okay, so in example 5, I say there's one exactly like this in the textbook. This is a little bit of a learn on your own, get to know your textbook. It's on page 89, so you could stop it and read this example, or get that example into your notes now if you like. But I am going to pick up example 6 and example 7 in part 3.